Okay, great. So let me just start with some announcements. On Slack, there's a link to sign up for student talks under physics chat. So you should go and do that. I think Casey Cartwright is one of the organizers. I think there's another organizer, but I'm not sure who it is. Maybe someone can let me know for student talks. So yeah. The other announcement is that there's new GatherTown link, which I'll post at the end of the lecture today. Oh, and also we won't be officially going to Gather after this lecture. There will still be the official Gather lunch, but we'll just hang out and ask Alex questions if he has time.
Good. That's immediately after.
Yeah, just immediately after. There might be some extra questions after, like we'll stop recording, and then students tend to hang out and ask questions if you have time.
Yeah, that sounds good.
Okay, so great. So let's give it over to Alex, who's going to give us take us on, I think, a really epic journey through AdS3 CFT2.
Okay, so you know, it's a pleasure to be here. I actually never attended TASI as a student. This is my first time lecturing, so it's so wonderful to finally be here in Colorado. I can see the mountains from here. You know, it's truly a sight to be seen. Good. So I'm going to be talking about AdS3 CFT2. You know, my plan is a little bit ambitious. Today, what I'm going to be doing is giving you what probably shouldn't be regarded as a primer on 2D CFT, but might be more of a CFT2 survival kit. I won't necessarily assume that you've seen two-dimensional conformal field theories too much before, but I'll really only be covering some of the basic elements that I'll be needing in order to sort of move on to our discussion of AdS-CFT and AdS3 as a two-dimensional conformal field theory, because really one could spend, you know, an entire lecture series just on two-dimensional conformal field theory. And then moving on tomorrow, I'll also be doing AdS3 gravity. I'll be sort of doing the quote-unquote basics of AdS3 gravity, you know, maybe 20th century perspective on AdS3 gravity, before moving on to the 21st century perspective on AdS3 CFT2 in the final two lectures on Wednesday or Thursday. So I'm going to be giving these lectures in a Blackboard style to try and keep things as informal as possible. And although I will be moving, I think, a little bit quickly today when I give a sort of basic, you know, primer on two-dimensional conformal field theories, that doesn't mean that I'm not open to questions and to interactions. So I encourage everyone to stop, interrupt me, ask questions, please, because you know, that'll help me gauge the level of the audience, what people may or may not be interested in hearing, and help me keep things sort of as fun as exciting as possible for everyone. Okay. So without any further ado, let's go ahead and get started. So two-dimensional conformal field theories are in many sense much like conformal field theories and quantum field theories in higher dimensions, but there's an added advantage, which is that two-dimensional conformal field theories are under much more control in general than CFTs in higher dimensions. And that allows us to understand both the structure of two-dimensional conformal field theories, as well as interesting things like the AdS-CFT correspondence in a huge amount of detail when we're talking about AdS3 CFT2 that really isn't available in higher dimensions. Okay. And so to begin, let's just remember that a two-dimensional conformal field theory is just a quantum field theory, much like any other, except it has an additional set of symmetries. And in particular, it's invariant under conformal transformations, which is to say, coordinate transformations, diffeomorphisms, that are conformal transformations of the metric in 2 dimensions, which is to say that leave the metric unchanged up to an overall scale transformation. That is to say, up to some sort of overall factor. Of course, a general conformal field theory we would assume would be Lorentz invariant, which means it would be invariant under coordinate transformations that leave the metric invariant. And for a conformal theory, we only require that this theory is invariant under transformations that transform the metric up to an overall scale factor, up to some overall factor, which would be some conformal reparameterization of the metric. So explicitly, let's imagine that we're in 2 dimensions. And so the metric in 2 dimensions, you would write it as dx squared plus dy squared. Or if we were to introduce a complex coordinate z, you could write it as dz bar. And then we would be interested in describing conformal transformations as coordinate transformations of this 2-dimensional metric. So for example, you could imagine a coordinate transformation where you start with your z coordinate, and then you go to some new coordinate, let's call it w, that's a function of our original coordinates. And then how does the metric transform? Well, dz goes to dw, which is the derivative of w with respect to z, plus the derivative of w with respect to z bar times dz bar. So if you were to take w to be a holomorphic function of your coordinate z, the metric in the w coordinates is just related to that in the z coordinates by an overall scale factor. So what does that mean? That means that the conformal transformations in 2 dimensions are holomorphic transformations of this complex coordinate w. So the conformal group is the set of holomorphic times anti-holomorphic transformations of the coordinates. And of course, this is a much bigger group than the conformal group in higher dimensions. So for example, I understand that Mukund gave some lectures last week on AdS CFT in higher dimensions. And in higher dimensions, the group of conformal transformations is 5-dimensional. It's basically SOD, 2. So it's the Poincaré group in 1 higher dimensions than it would be normally, but it's still a finite dimensional group. And it's this infinite symmetry algebra that lets us attack 2-dimensional conformal field theories with much greater power than we can in higher dimensions. In particular, this is an infinite symmetry group. And generally speaking, if you have an infinite number of symmetries, so a quantum field theory is a theory with an infinite number of degrees of freedom. If you have an infinite number of symmetries, you might hope that one of those infinities is bigger than the other infinity and that the theory is exactly solvable. And in many cases, it's true that you can use the infinite conformal group of symmetries to, in a very precise sense, exactly solve a 2-dimensional conformal field theory. So in order to understand this in a bit more detail, let's think about these conformal transformations in more detail. So an infinitesimal coordinate conformal transformation would be 1. So I apologize, my tablet updated itself this morning, which means that it's now interacting with me in a very strange way, which is why it's shifting all over the place. Let's just try this out. Sorry, 1 minute here. Okay, maybe that's better.
Excuse me, can I ask a question?
Sure, please do.
This might be a silly question, but can you say precisely what you mean when you say that a QFT is invariant under a certain transformation?
It's in the same sense that when we consider, for example, a quantum field theory in flat space, that means that the Lorentz transformations and the full translations are symmetries of the theory, in the sense that in the quantum theory, there are going to be Hermitian operators which act on the theory, which generate these symmetries, and which, for example, leave the ground state invariant, and the other states in the theory will transform in representations of these symmetries.
Okay.
Good. And I'll do this all quite explicitly in the next few minutes. So in order to understand these in a little bit more detail and to sort of address this question that was just asked, let's think about an infinitesimal conformal transformation. So this is going to take our coordinate z to a new coordinate, and I want this to be some sort of infinitesimal variation of our coordinate. And so that means I'm going to take w to be z plus some holomorphic function of z, which I'm going to be take to being very small, so I'll call it epsilon of z. And then, as always, a coordinate transformation is generated by a vector. And what is the vector that generates this coordinate transformation? So it's generated by the vector, which is epsilon of z times d by dz, which I'll just write with a script delta there. So there are clearly an infinite number of vectors that generate these coordinate transformations. So what I would like to do is take as a basis of these vectors things that I'll call ln, which will just be the powers, I'll imagine doing the polynomial expansion of this holomorphic function epsilon. And then we have correspondingly anti-holomorphic transformations generated by another set of vectors. So these are just the vectors that generate these conformal transformations. They're vectors in the sense of differential geometry or general relativity. And they obey an algebra that is easy to verify. This is a one-line computation known as the Witt algebra. In particular, if you look at the commutator of two vectors, then you just get another vector.
Alex, why is there no constant term in the expansion?
Well, it's at n equals to -1. That's a constant. Or perhaps you mean something else.
No, that's fine. I was just
sorry. I believe I used the word polynomial earlier. I shouldn't have used the word polynomial. Here, n is an arbitrary integer, so we would call it a Laurent expansion, not a polynomial expansion. Does that make you happier?
Yeah, though if this thing is supposed to be holomorphic, then why should there be terms with poles?
So right now, okay, let me get back to that actually. So at this point, I'm not going to assume that it's holomorphic everywhere. I'll allow a pole at the origin. Okay. If you wanted this to be globally well-defined, then of course you would need n bigger than or equal to -1. For that reason, what I've called the conformal group up above is really what we refer to as the local conformal group. That is to say, the group of conformal transformations thought of around as being smooth in the neighborhood of some point. But if you wanted to consider conformal transformations that are globally well-defined, then of course we would need to restrict our attention further. And we'll get to that in a minute. In particular, for example, as you've already noted, we would need to take n bigger than or equal to -1. It turns out that you would also need to take n less than or equal to 1 in order to be well-defined around the point at infinity, not just the point at 0. So in fact, maybe I'll introduce this now. So this also includes a subalgebra, which is generated by L0 and L plus or minus 1, which are regular at z equals 0 and z equals infinity. Okay. So in particular, you need L bigger than -1 to be regular at 0, and it's a straightforward exercise to check that these are the only ones that are regular at infinity. And the way that you would check this is by doing the conformal transformation. We take z to 1 over z and map 0 to infinity and infinity to 0. Okay. So here, throughout these lectures, I'm going to suggest a bunch of exercises. In lieu of giving homework, I'm going to suggest exercises as we go along. And this is one nice exercise. And moreover, you can also check. So these generate an SL2R times SL2R subgroup of the full sort of Witt algebra times complex conjugate of the Witt algebra. So here, the two SLRs are generated by L0 and L plus or minus 1, along with L0 bar and L0 bar plus or minus 1. These generate an SL2R times SL2R subgroup, but that SL2R times SL2R subgroup is just the set of conformal motions. That is to say, the set of globally well-defined conformal motions, or we should say perhaps conformal isometries of the sphere, which you could think of as the complex plane plus this point at infinity. Okay. And that's also a straightforward exercise. So exercise, write down the usual round metric on the sphere, define the conformal isometry group as the set of vectors that transform this metric, that preserve this metric up to an overall scale factor, and verify that this gives you SO2, 2. Good. Actually, I see I've secretly gone from Euclidean to Lorentzian signature here. I should really call this SL2C and SO3, 1. Okay. Fortunately, nobody caught me there. Good. Okay, great. Now, there's one important example of a conformal transformation. And one that's going to motivate us for really the rest of this lecture today, which is a conformal transformation where you take z to be e to the iw. And I want you to think of this as a map, a conformal transformation from the plane to the cylinder. So in particular, note that because z is single valued, w is going to be periodic with period 2 pi. So if you let w be phi plus it, that would mean that phi is a periodic variable. So it's a coordinate on a circle. So if you wanted to draw a picture, the picture would be one where you have a complex z-plane that gets mapped onto a cylinder where we're just doing a radial map where the lines of, say, constant t here are the circles that map to the circles on the cylinder. And the radial coordinate is something that I have called t here. Okay. So t here is a radial coordinate on the plane, which then becomes something like a time coordinate on the cylinder. So I encourage you to think of t as a sort of time coordinate. And in particular, because we're in Euclidean signature, we could think of it as a Euclidean time coordinate. But later on, when we consider the Lorentzian interpretation of two-dimensional CFTs, we'll do a coordinate transformation where we take t to it, and then it's going to be a genuine Lorentzian time coordinate. Okay. This picture is very important because it means that if you were to consider this conformal field theory and start with an operator in this conformal field theory and insert it at the origin, of the plane, then that's not going to turn into an operator on the cylinder because the origin has been mapped off to t goes to minus infinity. Instead, what it's going to do is it's going to change the state of the conformal field theory on the cylinder.
Sorry, can I ask a quick question?
Sure.
You said this t is Euclidean time, not Lorentzian time.
So far.
How do I see that? How do I know that?
Good. So exercise. Start with the metric on the plane, dz, dz bar. Compute the metric in the w coordinates. Write it in terms of phi and t, and look at the signature of the metric. Okay.
I see. Okay, thanks.
Good question. Any other questions? Great. So this leads to the sort of so-called state operator correspondence in conformal field theory, which means that local operators are in one-to-one correspondence with states of the conformal field theory on the cylinder. Okay. So let me give you the simplest possible example of that. So the simplest operator that we could imagine is the identity operator, the operator that does nothing. Okay. What does that correspond to on the cylinder? That's the vacuum state on the cylinder. Okay, the state with nothing in it. Right? But what other sorts of states could you have? Well, in any quantum field theory, so far, we've talked about the symmetry generators. And the symmetry generators will then become operators acting on the Hilbert space of the theory. So for example, a time translation generator becomes a Hamiltonian, an angular momentum generator becomes, or an angular rotation operator becomes an angular momentum generator, and so on and so forth. And indeed, the Witt algebra that we wrote down before includes things that you would call a Hamiltonian and an angular momentum generator. So for example, the operator L0, what was that? That is z d by dz. In terms of those radial coordinates that I called phi and t, they were d by d phi plus I d by dt. And for L0 bar, that's z bar d by d bar, that is d phi minus I d by dt. So in particular, that tells us that the generator L0 plus L0 bar, what is that? That's dz plus d by dz plus z bar d by dz bar. That's the generator of scale transformations on the plane, but it's also the generator of time translations on the cylinder.
Alex, the way you've written it here, it looks like it's 2d phi, which I would think would be the generator of rotations on the cylinder.
Oh, I'm sorry. That's because I
Yeah.
got a minus sign somewhere. Apologies.
I think W should be phi minus IT, because that's when
Okay.
t goes to minus infinity will be mapped to z equals 0.
Did I miss a factor of I somewhere? Yes. No, I included a factor of I here. Right. So I think W is 5 plus IT, the way that I've written it.
But then z equals 0 is mapped to t equals plus infinity, not
Oh, okay.
because
Yeah. Well, that sign is not going to matter too much. But the sign that I think Jonathan was mentioning was the one that the fact that I missed a sign here. Something like that. Okay, good. Something like that. Okay. Exercise. Fix all my signs. Great. But what does this mean? So the symmetry generator, little L0 plus little L0 bar, is a generator of time translations on the cylinder. Okay. What does that mean? That means when we quantize the theory, there's going to be a corresponding operator in the quantum theory that we would call L0 plus L0 bar. And what is that operator going to be? It's going to be the Hamiltonian of the theory. So it's going to be the Hamiltonian of the theory on the cylinder. So you might call it H. Or if you're thinking about it on the plane, you might call it the operator that generates scale transformations.
Can I ask about the Hilbert space H, like the way it's defined? Is it like uniquely defined by the choice of operators you include at the origin, or?
So the way that I'm thinking about this is the Hilbert space is the Hilbert space of the conformal field theory on the circle. It's defined by my conformal field theory. And there is a one-to-one map between operators in the CFT, local operators in the CFT, and the states of the theory on the cylinder. So for example, the identity operator is one such operator that corresponds to the vacuum state of the CFT on the cylinder. But other operators in the theory that of course would depend on what CFT we're thinking of will lead to other states on the cylinder. Good.
Okay, thank you.
Great, thank you. Okay. And similarly, the operator L0 minus L0 bar, that's d by d phi as a symmetry generator, but as an operator, it's going to be the angular momentum operator. Which we might call J, whose eigenvalues will be the spin of a state, in the same way that the eigenvalues of the energy of the Hamiltonian are the energies of states. Now, here is an amazing fact about physics that I think should be taught in elementary school, or at least in undergraduate, but nevertheless, nobody ever seems to learn it. And this amazing fact is that an algebra of symmetries will differ from the algebra of charges that generate these symmetries by what we call a central term. So in particular, what that means is that if you have some classical theory that is invariant under a bunch of symmetries that obey some algebra, and then you talk about a theory that possesses those symmetries are going to be generated by charges, that is to say, generated by operators in the quantum theory. But the algebra of those operators is not necessarily the same as the original algebra of symmetries. Okay? In particular, they can differ by the addition of a constant on the right-hand side of the algebra. So there's a famous example of this, one that everyone should work through one time in their lives, which is that the generator of Galilean boosts so if you have a particle moving in one dimension, then the generator of Galilean boosts is t times d by dx. And the generator of momentum, d by dx. So these commute as symmetries, right? D by dx commutes with d by dx. So these commute, but they are represented in the quantum theory of a particle, that is to say a non-relativistic particle, because we're talking about Galilean boosts, moving in one dimension by operators that obey k commuting with p is not zero. And in fact, what is it? It turns out to be a constant, which is the mass of the particle. Okay. So if you haven't seen this before, then a great exercise to do is to use the Noether procedure to compute the charges that generate Galilean boosts for a particle, non-relativistic particle in one dimension, and check that the Poisson bracket between this charge and the generator of angular momentum is non-zero and is the mass of the particle. Okay. So this is the first baby example of a central extension of an algebra of symmetries when it gets promoted to an algebra of charges. And when we talk about a conformal field theory, we started out with an algebra of symmetries that obeyed this thing that I call the Witt algebra. And in general, when you have a quantization of this theory into a genuine conformal field theory, you expect that there's also going to be a possible constant that you could add to the right-hand side of this algebra. So in particular, that the charges that generate these symmetries obey not just the Witt algebra, but a central extension of this algebra. And it is a straightforward, but not necessarily interesting exercise to determine what possible central extension you could add to this algebra. And it turns out that there's only one possible term you can add to this algebra. That is, say, one possible thing you can add to the right-hand side of this algebra, which is the thing that I've written on the right-hand side of this algebra here. It's parametrized in terms of a single unknown constant. So here, this is some sort of dimensionless constant that is referred to as the central charge of the theory. And at this point, it's just an additional parameter that can arise when you construct a conformal field theory in two dimensions. That is somewhat analogous to the mass of a particle that arises when you try and construct a non-relativistic theory of a single particle in one dimension. Okay. So the algebra that I've written down is known as the Virasoro algebra. And this thing that I've called C here is the sort of dimensionless parameter that is going to describe different possible kinds of conformal field theories. So let's stare at this algebra in a little bit more detail. So the first thing that you notice is that because Ln commutes with L0 to be n times Ln, what that means is that Ln lowers the L0 eigenvalue by an amount n. But remember that L0, or rather L0 plus L0 bar, is the energy of a state. So if you want energy to be unbounded, if you want energy to be bounded below, then you're going to run into a problem unless you have some reason that you can't act with LNs arbitrarily on states in the theory. But in fact, this relationship that I wrote down here, this commutator between Ln and L0 should remind you of something. It should remind you of the algebra obeyed by a simple harmonic oscillator. Okay? So A, the lowering operator of the simple harmonic oscillator, lowers the energy of the harmonic oscillator by 1, because the commutator of A with A dagger A is equal to A. Okay? And it turns out that the way out, but of course the energy of a harmonic oscillator is bounded below. And the reason why it's bounded below is that you can't act with A arbitrarily on states. And how do you know that? Well, you know that because A, in fact, is not a Hermitian operator. It has a conjugate operator, A dagger. And you construct the Hilbert space of the theory by starting with the state that is annihilated by A, that is to say the ground state, and then building a full Hilbert space by acting on it with A daggers. And it turns out that one can do exactly the same thing in two-dimensional conformal field theory. And we do so by defining Ln dagger, that is to say we define an adjoint operation for our Virasoro algebra, and we define Ln dagger to be L minus n. Okay? Note that this is exactly the clever thing to do, because if L0 is a Hamiltonian, then it means that that Hamiltonian is self-adjoint. And indeed, we can check that this is the right thing to do, and I'll suggest this as an exercise by remembering that when you take t to minus t, that is the thing that is supposed to introduce, when you represent t as a Hamiltonian, h is I d by dt. Taking t to minus t is the time reversal operation that takes operators to adjoints of operators. And you can check using the expressions I gave earlier for these Virasoro generators that taking t to minus t takes n to minus n. Okay. Once we do this, however, what you see is that we can organize the spectrum into representations just like in the simple harmonic oscillator that are built on states that we will call primary states that are basically the analog of the ground state of the simple harmonic oscillator. So in particular, they will be eigenvalues of L0 with some eigenvalue that I'll call H, and they are going to be annihilated by all of the lowering operators. And then,
hi, sorry, can I ask a
yes,
question?
sure.
Just to be clear, so ln dagger will be different from LR.
So yes. So remember that I introduced factors of I in defining my complex coordinates, right? So I had Z's and Z bars. Those are just two different coordinates. So for example, L0 bar generates one kind of coordinate transformation that differs from L0, okay? But that bar has nothing to do with the adjoint of this as a quantum mechanical theory, okay? In order to understand what operation corresponds to the adjoint of the quantum theory, you think about what it means to take t to minus 2, okay? Which is how you would get ln is minus ln bar, ln dagger.
Okay, so yeah, so the usual intuition that you also complex conjugate the numbers won't work here, because you shouldn't take z to z bar, for example.
Yes, z to z bar is a coordinate transformation on the space that the CFT lives on that is distinct from the adjoint operation acting on, for operators that act on the Hilbert space of this theory. Good. Is that
okay, thank you.
Reasonable? Okay, great. Good.
That helped, yes.
Great. So how would you build the representations that states in the theory live in? Okay. So a full representation will be built by acting with a bunch of these Virasoro operators on some primary state. So this is what is known as the Verma module.
I have a quick question.
And yes, let me just finish the sentence. It's the thing that is spanned by a bunch of the corresponding raising operators acting on one of these primary states. And the states that you obtain by acting with these guys on the Virasoro, the primary state, are known as descendant states. Yes, question.
So there are an infinite number of primary states?
Well, it depends what sort of theory you're in. Some theories will have a finite number of primary states and some will have an infinite number of primary states. And in fact, that's the next thing that I was going to get to.
Okay, thank you.
Good. Great. So in particular, it's a straightforward exercise now. So I'll suggest it to you as an exercise. To compute the norm of L minus N acting on some state, right? How do you do that? Well, you use the fact that L minus N dagger is Ln. So this is a straightforward calculation using the Virasoro algebra. It's a pretty simple calculation. But this result is an incredibly important result because immediately we can then use unitarity in order to understand what sort of representations are allowed. In particular, unitarity says that all of the states in the theory must have non-negative norm. They should generally have positive norm. So what does this tell you? So the first thing it tells you is that the number on the right-hand side here must be a positive number, okay? So taking n large here would then tell us that the central charge must be greater than or equal to 0 in order for this to be a positive number. The next thing you see, taking n equal to 1, is that the dimension h must be a positive number. And the final thing we see is that if h is equal to 0, then L minus 1 acting on the state with H equals 0 will be equal to 0. In other words, the state with H equals 0 is annihilated, if I can spell that correctly, by the generators of the global conformal group. What does that mean? The state with H equals 0 is the thing that's obtained by acting with the identity operator at the origin of the plane, right? Because the identity operator is scale invariant and it's rotationally invariant. So it has L0 and L0 bar equal to 0. That's the thing that we call the vacuum in the language of the CFT on the cylinder. And what we've seen here is that the vacuum is invariant under the global group of transformations, okay? So the vacuum is SO22 invariant, but general primary states with dimension bigger than 0 are not going to be invariant. Okay? Now, there was a question earlier about when, whether we have an infinite or a finite number of primaries. And it turns out, and this is just something that I'll quote to you as a fact, and it's a fact about the representation theory of Virasoro algebra, which is that when the central charge is less than 1, there will be negative norm states unless the central charge takes one of a particular set of values. And H takes one of a finite number of values. So that means that in such theories, there can only be a finite number of primary states. Okay? And then those are theories where you have a symmetry algebra that's so big that even though a quantum field theory has an infinite number of states, there are only a finite number of representations of the symmetry algebra. Okay? So effectively, once you've incorporated the effect of symmetry in the theory, there are only a finite number of states. So such theories where C is less than 1 are theories where the power of conformal symmetry is enough that you've basically reduced everything to a finite number of degrees of freedom. So these are conformal field theories that are much closer to quantum mechanics systems in their complexity, finite dimensional quantum mechanics systems, than to full quantum field theories. And so these are what we would refer to as rational conformal field theories, because the value of the central charge is a rational number. Okay? And they are essentially integrable. But the converse of this fact is that if the central charge is bigger than 1, the theory has no null states aside from the one that we've already discovered, which is L-1 acting on the vacuum. Okay? And in particular, such theories typically have an infinite number of primary states. And they're generally called irrational conformal field theories, unless you happen to have some extra symmetry somewhere that allows you to solve the theory. They'll typically have an infinite number of primary states. And unlike the integrable rational CFTs, generically, they're going to be chaotic. Okay? So these are the two-dimensional conformal field theories that are similar in spirit to higher dimensional conformal field theories, to genuine sort of chaotic, complicated, strongly coupled systems.
How many primary states do you have at C=1?
At C=1, that's a great question. In some sense, that's the thing that we're going to return to in the final lecture of this week. Essentially, the C=1 theory is on the cusp of being chaotic. It's a boundary case between being an integrable theory and a rational theory. There's a sense in which C<1 theories have a finite number of states. C>1 theories have an exponentially large number of states, and C=1 theories have a polynomial number of states. So you still have an infinite number of primary states, generally speaking, but they're much easier to study than the C>1 theories.
Okay, thank you.
Great question. Yeah.
Can I ask a question?
Yes.
So you mentioned that like the rational CFTs are integrable. Can you be more precise on what you mean by integrable theory?
What do I mean by integrable? I'm intentionally not defining what I mean by integrable exactly. So the standard way that, I think maybe Poincaré defined an integrable theory is that an integrable theory is one where the number of degrees of freedom is equal to the number of conserved quantities, right? Because that allows you to solve the theory exactly. If the number of conserved quantities is equal to the number of degrees of freedom, then you solve the theory exactly. The problem is that in a quantum field theory, you have an infinite number of degrees of freedom. In a conformal field theory, we have an infinite number of conserved quantities, okay, right? We have an infinite number of Virasoro charges. So the question is whether infinity is bigger than or less than infinity, right? So, sometimes people will say that every conformal field theory in 2 dimensions is integrable because there's an infinite number of conserved quantities. That's really not, I think, the right way of thinking about it. Instead, the way that I would think about it is, do these symmetries let you solve for the theory exactly? Okay. And it turns out in the case where C is less than 1, the answer is yes. So as an exercise, something that I'll suggest is, so up above, I suggested that you do this computation. Okay, compute this guy. Here's another computation you could do. Study the 2x2 matrix of inner products of all of the states that are descendants at level 2. That is to say, they're either obtained by L-1 squared or L-2 acting on a primary state. Demand that that thing has all of the states at level 2 have positive norm and see what kind of constraints you get on the spectrum. Then demand that some of the states, that all of the states have a descendant with 0 norm and see what constraints you get on the theory. And in particular, you'll see that if you take the m=3 value of this, so that C is equal to 1/2, or sorry, maybe that's m=2. M=2, so that C is equal to 1/2. You'll see that there are 3 possible values of the dimension where there's a null state at level 2. And these have h=0, h=1/16, and h=1/2. Okay. And what are those? Those are the critical exponents of the Ising model. Okay. So that's an example of an exactly solvable theory, where by just studying the Virasoro algebra, you immediately derive the possible set of allowed energies in the theory, which in the scaling interpretation of the CFT on the plane is the set of allowed scaling dimensions. And in fact, you can match this exactly with the 2D Ising model, which is exactly solvable. Okay. And so I'm not going into much detail here, but that at least gives you some flavor for how we use this Virasoro symmetry to exactly solve these theories. When I write up these lectures a little bit more carefully, I'll include that as an exercise that you guys could do.
Yeah, by the way, C is 0 and M is 2. So you might
Sorry,
want,
I can't hear you.
the C is 0 and M is 2, so you might want to set M is 3.
Sorry, it's very
He's just
quiet.
saying m=3 is C=1/2, not m=2.
Oh, what's it? M=.
Yeah.
Oh yeah. Okay, great. Good. Oh, there's a factor of 6. Great. Okay, good. Okay. Yeah, sorry, m equals 2 is the Li-Yang model. Good.
No, the Li-Yang model is the 2-5 model. No, that's non-unitary.
Oh, yes. Okay, 2-5. Right. Sorry. Okay.
No worries.
Okay, so there are a lot more things that one can say. You know, there are an infinite number of things that one can say about two-dimensional conformal field theories. Let me make one more comment, which is that if we were to study the energy of a CFT, of the CFT ground state, on the cylinder, it turns out that this is not 0, but because of the Casimir effect, it is going to be negative. And it turns out that it's equal to minus C over 12. Okay. So one can go through a derivation of this. The derivation of this essentially uses the behavior of the transformation of the energy under conformal transformations. And it turns out that generically, the energy of the vacuum state on the cylinder is determined only in terms of this central charge term. So it's minus C over 12. Okay. I'm not going to prove this for you in the interest of time. Instead, I'm going to assign it to you as an exercise by way of an example. So a simple example of a two-dimensional conformal field theory with central charge 1 is a free boson. So in particular, if you so possibly the simplest conformal field theory in 2 dimension that you could imagine writing down is the theory of a free boson. Okay, here it's a massless free boson since you want the theory to be conformally invariant. And so it has an action, which is the usual action of a massless free boson. So of course, as you're probably familiar with from your knowledge of field theory, if you take a free boson on a circle, just like if you took electromagnetism on a circle or between 2 parallel plate capacitors, there's a negative Casimir energy. And so an exercise that I think is a good exercise to do is just to compute the Casimir energy on a circle of radius 2 pi and show that the energy is minus 112. Okay. So of course, formally speaking, Casimir energies, as always, diverge. So one needs to regulate in some way. If one uses zeta function regularization, essentially using the very famous formula that 1 plus 2 plus 3 and so forth is regularized to minus 1/12, then you show that the Casimir energy of a massless scalar field on a circle of radius 2 pi is minus 1/12. And that's one example of this observation that, or this fact that I have quoted for you, that in a conformal field theory, the energy of the vacuum state on the cylinder is not 0, but in fact is given by the central charge. So there's one more powerful constraint of conformal invariance that can be used to constrain the behavior of conformal field theories. And that's the constraints of modular invariance, which were used by Carty in order to understand the high energy behavior of conformal field theories. That's the next thing that I wanted to do. I see that it's already 11 o'clock. So what I don't know is whether I'm honestly supposed to go to 11:15 or whether that last 15 minutes should be reserved for questions. So maybe
yeah.
Maybe I'll ask.
We've been going to 11:15 and then having a
Okay.
couple of questions that are recorded and then
Okay, that sounds good. Okay, so maybe that's where I'll head next. Okay. So far, what I've done is I've used the invariance under local conformal transformations to talk about how the spectrum of the theory is constrained. You know, we learned that C is bigger than 0, that all the H's are positive, that states are built in representations of the Virasoro algebra. But it turns out that you can use conformal invariance to really constrain the theory much more strongly. And my favorite example of that, and the example that's going to kind of motivate all of us in our understanding of CFT2 AdS3, is how we use conformal invariance to constrain the spectrum of the theory. And in particular, the spectrum of a two-dimensional conformal field theory is captured by the partition function. So here, I'm going to define a partition function. So what I would like to do is define some function that counts the spectrum of the theory, that captures the spectrum of the theory. So in particular, you know, L0 and L0 bar are the generators of time translation and rotation. Okay. So what I've written down here is the trace of Q to the L0, Q bar to the L0 bar, traced over the Hilbert space of the theory, where I've just introduced some random parameter Q that, for the purposes of making this sum convergent, so this is going to be a sum over all states in the theory of Q to the L0 times Q bar to the L0 bar. And in order to make this convergent, I'm just going to choose Q to be some complex parameter whose modulus is less than 1. Okay? Now, if you wanted to write this in a way that is a bit more familiar to you from thermodynamics, we would remember that L0 plus L0 bar is the Hamiltonian, and L0 minus L0 bar is the generator of rotations. So you could write this as the sum of e to the minus beta h, where h is the Hamiltonian of the theory, and theta, it would be something that would be like a thermodynamic variable conjugate to angular momentum. So here, we conventionally write Q is e to the 2 pi I tau, where tau is some complex parameter, and tau would be related to the inverse temperature and angular potential by tau being 1 over 2 pi plus I times the inverse temperature. Okay. So this is the finite temperature partition function of a two-dimensional conformal field theory. But this is also the partition function of the theory on a torus. How do you see that? Well, we just remember that the operator e to the minus beta h is the operator that generates time translation. There's no factor of I because we're in Euclidean signature. And it generates a time translation by an amount beta. So what's going on here? We're starting out with the CFT on a cylinder. And you act with e to the minus beta h. That translates you in time by an amount beta. You also act with the operator e to the I theta j. That generates a rotation of your angle phi by an amount theta. And then when you take a trace, you glue together the top and the bottom of the cylinder to get a torus. Okay? And in particular, if theta is not 0, you're gluing them together with a relative twist by an angle theta. Okay? So the torus partition function of the theory is the same as the finite temperature partition function of the theory on a cylinder. So in order to write that a little bit more clearly, what I'd like to do is define a complex parameter, a complex variable, as before, which is phi plus IT. And then the torus is defined by the relation that W is W plus 1, because phi is periodic with period 2 pi. And it's also identified with W is W plus tau, just because I'm doing that translation by an amount e to the minus beta h. Okay. Good. Or to write this a little bit differently, W is identified with W plus n tau plus m for any integers n and m. Or W is identified with W plus a vector of integers, n, m, contracted with or dotted into a vector with components tau 1. Okay, good. Everyone with me so far? So here I'm just noting that the finite temperature partition function is the partition function of the theory on a torus. And I've defined my torus on the complex plane in terms of the identification of W by shifts by 1 or shifts by tau. Okay. Now I'm going to do an incredibly sneaky trick. Okay. So you know, I have nothing hidden in my sleeves, right? But I'm going to do an incredibly sneaky trick. What I'm going to do is I'm going to note that I could always take some invertible matrix of integers. That is to say, I could take some matrix of integers valued in SL2Z, that's the name for the group of invertible matrices of integers. And I could always relabel my parameters n and m. So all I'm doing here is relabeling my basis of integers. So instead of labeling them by n and m, I'm going to multiply that times some invertible matrix, label them by some different set of integers. And then if I were to do that, I would identify the torus as follows. So I haven't done anything yet, and I'm not going to do anything, right? All I'm doing here is I'm relabeling the set of integers that I use in order to define my parameters on the torus. But now I'm going to be very sneaky, and instead of multiplying that invertible matrix on the nm on the left, I'm going to multiply it on the tau 1 on the right. Okay? So I have an a tau plus b and a c tau plus d. Or what I'm saying is that the torus that I'm looking at could also be defined by the identifications where you identify W with W plus a tau plus b and c tau plus d.
Alex, you have 5 minutes.
Thanks. Or if we wanted to rescale, so remember, we only care about things up to conformal transformations. So I could always divide my W coordinate by C tau plus D. And if you did that, you would see that now my torus is defined by a set of identifications where you identify W with W plus 1 and W with W plus A tau plus D, A tau plus B over C tau plus D. Okay. So
Sorry,
what
why
does
can you
that
take this
mean?
ratio? Why can you take this ratio of A tau plus? Why are you allowed to do this? I got
Because
confused.
remember, we're studying a conformal field theory. And on a conformal field theory, you can always rescale your coordinates and the theory doesn't change, right? Everything is invariant under this conformal transformation. So multiplying my coordinates phi and t or my coordinate w by a constant doesn't change anything in the theory, right? The partition function, for example, is invariant under rescalings of coordinates. That's
Okay.
a conformal symmetry of the theory.
Mm-hmm.
Here, I'm using a conformal symmetry where I multiply my coordinate w by 1 over c tau plus d.
This is true on torus as well. This is true on torus.
Yeah. So in some sense, this is a new use of conformal symmetry aside from the ones that we've been using previously. So what we conclude here is that the torus defined by the parameter tau, known as a modular parameter, which is related to the temperature by this factor of 2 pi, is the same, I should say, up to a conformal transformation, is conformally the same as that defined by the modular parameter that we denote gamma tau, which is A tau plus B over C tau plus D. So this is an example of a use of a conformal transformation that goes beyond the Virasoro algebra. The Virasoro algebra defines what we call local conformal transformations. This is what we might call a large conformal transformation. It turns out that this is a invariant. We're using the invariance of the theory under conformal transformations, but these are not conformal transformations that are continuously connected to the identity. Okay, that is to say, they are not conformal transformations that can be deformed to be trivial. So they give us new constraints on the theory. So the most interesting such constraint is the one where we take tau to minus 1 over tau, which, if you were to set theta equal to 0, is beta to 4 pi squared over beta, because I've introduced that factor of 2 pi in my definition of tau. So what does this mean? This means that the finite temperature partition function of a conformal field theory is invariant under temperature to 1 over temperature. I mean, that's nuts, right? In what universe would you have a theory where the finite temperature partition function is invariant under temperature goes to 1 over temperature? It means that the high temperature of the behavior of the theory is determined by the low temperature behavior of the theory. In particular, the low temperature behavior of the theory, so that would be when inverse temperature goes to infinity. What is the low temperature behavior of the theory? Well, it's e to the, remember, the partition function of the theory is the sum over states of e to the minus beta h. So at low temperature, that's going to be dominated by the energy of the vacuum state, right? The lowest energy state in the theory. which is e to the beta c over 12, right? Because I told you earlier that the ground state energy of the theory on a cylinder is determined by the central charge. And you checked it, or you will have checked it for a free boson of central charge 1. But this
Sorry, can I ask
means...
a question?
Sure.
For the conformal invariance of the partition function, is it exactly invariant or invariant up to an overall C number?
Generally speaking, we're not so persnickety to care about overall numbers in our partition function. There's a subtlety, having to do with the Weil anomaly, which is that partition functions are not numbers, but in fact, you should think of them as sections of line bundles. So from a to be mathematically precise, the partition function is not a number, but a section of a bundle that has an overall factor of the set. It's a section of a bundle, which is the product of some bundle to the central charge power. It turns out for the torus, this doesn't matter, and that you can set everything up so that the torus is indeed exactly modular invariant. At some point, if I get distracted, I might talk about higher genus partition functions of conformal field theories, which are not numbers and are ambiguous up to an overall factor in this way. But for now, for the torus, it's perfectly safe to think of the partition function as a number that is modular invariant. Good question.
Even for rescalings of the torus, not just
even for rescalings of the torus.
Even for rescalings of the torus. I see. Okay. I guess because it's flat.
Yeah. Okay. That's exactly right. That's exactly right. So for example, there are other parameterizations of the torus for which you would have what we would call conformal anomaly factors out front. Okay. Good. I haven't really discussed the conformal anomaly, so maybe we can defer that. In any case, I have -3 minutes left, which is just enough time for me to get to the punchline. So the punchline is that given that we have the low temperature behavior of the theory determined in terms of the Casimir energy of the ground state, and we have modular invariance, which relates the low temperature behavior to the high temperature behavior, the partition function of the theory at high temperature is then given by this formula. So we have an e to the 4 pi squared over beta times c over 12, otherwise known as e to the pi squared over 3 times c over beta. So what does that mean? That means that the high energy density of states is completely fixed by the conformal anomaly coefficient, by the central charge. And in general, we see that the energy of the ground state determines the high energy behavior of the theory. So here I've written down the partition function of the theory. It's straightforward to go from there to the density of states. Okay. So in particular, since the partition function of the theory is related to the density of states by this Legendre transformation, in order for this to go like e to the c over beta, at high energy, that determines the behavior of the density of states at high energy. And in particular, what you find is that the density of states, this is just a straightforward calculation, goes like e to the 2 pi square root of C times E over 3 at high energy. So here, I'm using a kind of mixed notation here. So if I'm thinking about the CFT on a cylinder, then I call L0 plus L0 bar E. But if I were to think about it on the plane, I would call L0 plus L0 bar delta. So E is the same as delta. So in particular, what we've seen is that we've been able to predict the number of operators in the theory with large scale scaling dimension, or on the cylinder, the number of states in the theory of very high energy. And we've done it just using conformal invariance. And we've found a universal answer that's determined by the central charge. Okay. So there's one more exercise, and this is probably the most important exercise that you can do, which is to check this. By doing the integral dE using a saddle point analysis. At large E. I mean, it's a 2-line calculation, right? You take that expression for the density of states, you find the saddle point, you solve for it, okay? And in particular, what you'll find is that the saddle point is at a value of the energy that becomes large as the temperature is becoming large, right? So it's going like 1 over beta to some power. Okay. So what have we done here? We've determined the entropy of a 2-dimensional conformal field theory at high energy. And we found that the entropy goes like e to the 1/2. Okay. I'll make one final comment, which is that in general, just on the basis of dimensional analysis, you can always conclude that in any conformal field theory in d dimensions, the high energy entropy is going to go like e to the d minus 1 over d. Okay. Exercise proved that using dimensional analysis. Right. The truly remarkable thing that distinguishes 2D CFTs from their higher dimensional cousins is that we can determine the coefficient that goes in the front there. And it's just given by this central charge. All right, I apologize for going over time, and I'll stop here and see if there are any questions.
Thanks, Alex. I suggest actually, because of the time, let's just go to break, and if people want to hang out and ask questions, then
So is the break in Gathertown? Is that where it is?
Well, it's not officially, but unofficially, yes, students can go there. But if you could hang out and if people want to hang around and ask you questions.
Okay, am I hanging out here or am I hanging out in Gathertown?
Yeah, just in Zoom.
Okay. Yeah.
For now, basically, I think this will be cut out of the recording. That's the only difference.
Okay, sounds